So we've covered how to do significance testing with proportions. Now it's time to do it with means. This is what we're going to try to do in this section. We're going to check the conditions for carrying out a test about a population mean, random, normal, independent. We're going to conduct a one-sample t-test about a population mean, and construct a confidence interval to draw a conclusion for a two-sided test about a population mean. So just like it was with the proportions, there's a close relationship between a confidence interval and what it contains and the values that a significance test would cause us to fail to reject in that case, but more on that later. And also perform significant tests for paired data, because comparisons is often what we'll want to look at. Alright, so we know confidence intervals and significant tests for a population proportion, P, are based on z values from a standard normal distribution. But inference about a population mean, mu, has to use the t distribution with n-1 degrees of freedom, since its distribution tends to not quite be normal, except in the rare case when we know the population standard deviation. If that happens to be true, then we can use z-scores. Now, we learned how to construct confidence intervals for population mean back in section 8.3. So now we'll examine how the testing a claim about an unknown parameter mu will work with significance testing. We had an earlier example where we were looking at AAA batteries, and the companies said they made some new ones that should last longer. Their regular AAAs last for 30 hours of continuous use on average. And a simple random sample of 15 new batteries that they're hoping will last longer, their simple random sample of 15 of them lasted an average of 33.9 hours with a standard deviation, that's the sample standard deviation, of 9.8 hours. Here's the question. Do these data give convincing evidence that the new batteries last longer on average? Because remember, what we have to decide is this actually a fairly likely thing that would happen even if the mean still is 30 just because of sampling variability? Or is it true or convincing evidence that this is not likely to happen if the mean was just 30 and it is likely the mean is more? So similar to the way we did it before, we start by picking our hypotheses. The null hypothesis would say that mu is 30 hours. The null is basically the idea of no change or no difference from what was before. But we hope, or the company hopes, that the mean is now greater than 30 hours, so that will be our alternative hypothesis, where mu equals the true mean lifetime of the new deluxe AAA batteries. So we do have to make sure we have defined what mu is. Then we check the conditions, same as before, random, normal, and independent. Keep in mind, the normal condition when we're dealing with means is either that the population distribution is normal, or that the sample size is large, which we define as 30 or bigger. If the sample size is small, we actually have to examine the sample data. We can use a histogram, box and whisker plot, dot plot, or a probability normal. The word's on the next page. I'm losing it at the moment. Anyway, I think it's probability distribution plot. But anyway, we have to examine that to see how far away it is from normal. If there's some strong skewness or outliers, then we've got to probably say, no, we can't use this normal condition. So just a reminder, this slide is actually just a copy of one we've had before, but I wanted you to remember how we deal with it when we have samples that are smaller than 30. So you see in the first one there it says, if the sample size is less than 15, then we can only use t procedures if the data appear close to normal, meaning roughly symmetric, single peak, and no outliers. It doesn't have to be exactly normal, but it has to look pretty close to normal. And if there's skewness or outliers, then we can't use t procedures. If the sample size is between 15 and 30, then the t procedures can be used except in the presence of outliers or strong skewness. So the data doesn't have to look as close to normal, but if we see strong skewness or outliers, we still have to throw it out. But then with large samples, even if it's skewed and has outliers and such, as long as we are 30 or bigger in our sample size, we are good to go for using the T procedures. So let's keep on with our battery question. So checking these conditions. Random, they took an SRS of 15 new AAA batteries, good to go. Normal, so since the sample size was 15, we do have to look at the data. You can see a dot plot and the normal probability plot. That's what I was trying to think of. That's on the far right. And the box plot is in the middle. They show some slight skewness, but certainly not strong skewness, and no clear outliers either. So this is okay. The normal probability plot is pretty close to linear, so everything is telling us using T procedures is good to go. We can call it normal enough. And independent. Since the batteries are being sampled without replacement, we do need to check the 10% condition, so there would have to be at least 10 times 15 or 150 new AAA batteries, and considering this is a company that makes them, that seems pretty reasonable to guess they'd make at least that many. Then we've got to figure out our test statistic. So this has the same basic format as it did with proportions. We do a statistic minus the parameter over the standard deviation of the statistic. Let me pause here. I may be going too fast, and if so, I apologize. But please keep in mind you are welcome to pause this video at any time, allow you to catch up in writing, or just to keep me from talking way too fast and way too much. So we have the statistic, which is going to be x bar in this case, minus the parameter, which is going to be the mu that our null hypothesis assumes, over the standard deviation of the statistic, which is right there, just as we've used before. So the sample standard deviation for a mean. So the t value you see down below is what we'll use for the means. X bar minus mu naught over the sample standard deviation. We have to use Sx instead of sigma because we don't know sigma. And then square root of n, our sample size. So when our conditions are met, the statistic has a t distribution with n minus 1 degrees of freedom. Moving right along. So for the battery company, notice we do need two pieces of information from the sample. We need its sample mean, which they gave us is 33.9 hours, and the sample standard deviation, 9.8 hours. We need both of those. So then we can compute the test statistic. We do our x bar minus the mu that the null hypothesis assumes, which is 30. Then we do the sample standard deviation over the square root of the sample size, 9.8 over square root of 15, and we get a t statistic of 1.54. Just a reminder, that's saying we are 1.54 standard deviations above the mean. Now we'll find our p-value. That's the probability of getting a result this large or larger. Don't forget, when we're doing significance tests, we're always saying what's the probability of it getting this far away or farther away. So in this case, this large or larger. Or if it's on the other end, if it was below it, it'd be this low or lower. But we need to find the probability in a t distribution of t being greater than or equal to 1.54. You can use table B to do that. We go to the degrees of freedom 14, and we look for the value that's closest to 1.54. And we can see that falls between 1.345 and 1.761, and that tells us our value of p has to be somewhere between 0.05 and 0.10. So it's above 5%, below 10%. So that means the p-value is bigger than 0.05. It's got to be because it's between 0.05 and 0.10. Because the p-value exceeds our default alpha equals 0.05 significance level, we can't conclude that the company's new AAA batteries last longer than 30 hours on average. So once we do this in the true four-step form, which we all know and love dearly, we really need to say something about the null, which would be we fail to reject the null because our p-value is greater than the 0.05 significance level, and then we don't have sufficient evidence to conclude that the company's new AAA batteries last longer than 30 hours on average. So notice we're really saying something about both the null and the alternative hypothesis. Whew, deep breath. Let's roll. Reminders about using table B, I would actually just say don't, because you can use TCDF in your calculator. But just in case you ever need to use table B, or in case you just enjoy those tables, want to give some reminders. We do have limitations in the sense that it does not show every possible degree of freedom. It goes from 1 to 30, but then skips to 40, 50, 60, 80, 100, 1000. So if the degree of freedom we have for a problem is not listed there, we always go to the one just below that number. So for example, if we have even 39, we don't go up to 40. I know it's close to 40, but you never go up. You always go down. You go to 30 in this case. So always use the next lower degree of freedom that is available. And a good reminder here is that table B shows probabilities only for positive values of t. So if we are ever dealing with something being lower than our mean, we're going to get a negative t value, but that's fine. You just convert it to the positive and look for that. Since the t distribution is negative, for example, finding out the probability of it being below -2 is going to be the exact same value as finding the probability of it being above +2. So below -2 and above +2 is going to be the same values. So we just always stick with the positive form of our t when we're looking in the table B. So here they give suppose you're performing a test. This is saying a lot of the same stuff I just mentioned. So if we had a t value, you can see, of -3.17, there's no negatives in the table B, but that's fine. We just look for the one that's positive 3.17, because that'll give us the exact same value for p. So we would know in what they've set up here that the value would be between 0.0025 and 0.001, because you can see the graph is symmetric. Okay, and good note here, we'll talk more about two-sided tests later, but since this was a two-sided test that you look up top, their alternative hypothesis was that mu does not equal 5. Once you find that range, that 0.0025 to 0.01, you then have to double those because we're doing two-sided, we're doing both sides. We want to know the probability of it being below -3.17 or 3.17 and above. So it goes on both sides, so we do have to double our p-value. Alright, the one sample t-test. When the conditions are met, we can test a claim about a population mean, mu, using a one sample t-test. So here's most everything we've already said, but just laid out in one place. So we'll choose an SRS of size n from a large population that contains an unknown mean mu. We want to test the hypothesis that claims that mu is equal to, the true mu in other words, is equal to the mu claimed in the null hypothesis. And we compute the one sample t statistic, which you can see there, we've talked through that already. Then we find the p-value by calculating the probability of getting a t statistic this large or larger in the direction specified by the alternative hypothesis in a t distribution with degrees of freedom n-1. So you can see on the left, with the greater than, we want that t value or greater. In the middle, less than, we want that t value or less. And then the two-sided, the where it's not equal to, on the far right, we want to know both. Bigger than the absolute value of t or less than the negative version of t. We add those together. Alright, here's our example we're going to run through with a true four-step process. So the level of dissolved oxygen in a stream or a river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results. Don't worry, I'm not going to read those out. A dissolved oxygen level below 5 milligrams per liter puts the aquatic life at risk. So that right there should clue you in on what we want our hypotheses to be. So as far as our state, we want to perform a test at the alpha equals 0.05 significance level, where we're considering where the null hypothesis, mu equals 5, and the alternative hypothesis that mu is less than 5. Since it's less than 5 that gives danger to the aquatic life, that's what we care about. That's what we want to check. And we have to define our mu, just like with proportions, we have to define our p. It's the actual mean dissolved oxygen level in this stream. Sorry, those are overlapping there. If the conditions are met, we should do a one sample t-test for mu. If the conditions are met, we do a one sample t-test for mu. Random, we're good there. We're told randomly chosen. Normal. The size does not allow us to just say check, we're good, because it's not 30 or bigger. So we do have to look at the data. You can see down in the lower right the histogram, the box plot, and the normal probability plot. And those are all relatively close to normal. That's pretty close. No clear strong skewness or outliers, so we're good to go there. It's safe to use the T procedures. And there's just describing those. And independent. Really, there's an infinite number of possible locations along the stream, so it isn't really necessary to check the 10% condition. Because if there's an infinite number of possibilities, then no matter how many we take, there's always 10 times more possibilities. We do have to assume that individual measurements are independent. What we're communicating there is we do have to assume that when we take a measurement in one area of the pond, it in no way affects our measurement in another area of the pond, which, considering we're talking about moving water, seems pretty reasonable. Do. Well, notice we need two sample pieces of information here, the mean, the sample mean, and the sample standard deviation. And just a reminder, you can find these in the calculator. Now I know they just gave us this list of 15 back here, but if you put those in stat L1 and then run the one variable statistics, it will give you these two numbers, the sample mean and the sample standard deviation. Once we state those, we find our test statistic, plug in all our values, our x bar, our mu naught, our sample standard deviation, and our sample size. We get negative 0.94. So then to find the p-value, we want to know the area to the left of t equals negative 0.94. You can do this with TCDF. That's what I'd recommend. It's going to give a more exact answer anyway. But with table B, you would just look for positive 0.94, where the degrees of freedom is 14. And since they've got table B up here, we'll look there and we'll see that it's going to fall somewhere between 0.20 and 0.15. So that is certainly giving us a p-value that is greater than 0.05. So we conclude that the p-value is greater than alpha equals 0.05 significance level. So we fail to reject the null hypothesis. We don't have enough evidence to conclude that the mean DO level in the stream is less than 5 milligrams per liter. So again, I wanted to point out that in the conclusion, I don't think I emphasized this well enough in the proportion notes. I apologize for that. We need to make a statement both about the null hypothesis, in this case, that we failed to reject it, and about the alternative. We don't have enough evidence to conclude that the mean DO level in the stream is less than 5 milligrams per liter. So we fail to reject the null, meaning we don't have enough evidence to accept the alternative. So since we failed to reject the null, that leaves a possibility of a type 2 error. Doesn't mean we did make one, it just means that's the thing we could have made because we failed to reject. It could be we failed to reject the null when the null actually is false. And if we did, that would mean the dissolved oxygen level mu in the stream is actually less than 5 milligrams per liter, but we didn't detect that with our significance test. So here's the required pieces of the four-step process when we're doing significance tests for means. So I'm not going to walk through that with you because you have it there and you'll have examples showing the same thing, but you have it in your notes anyway. And it's pretty similar to what we did with the proportions. So the only differences that really jump out with me is that in do, you do have to have two sample statistics, the mean and the standard deviation. We only had one with proportions, p hat. Also, we're using t distribution instead of z. And what I tried to make more clear and better here is that in our conclusion, like I've said a couple times already, we need to make sure we make a statement both about the null, whether we reject it or fail to reject it, and whether there is or is not sufficient evidence to agree with the alternative hypothesis's claim. In good news, we can calculate the p-value for this in our calculators using, you know it, the t-test. I'm going to briefly show you here, but you can look at page 573 for more on this. So just to make sure you see it, I'm under t-test. Let me show you how you get there. We go to stat, shocking, go over to tests, and we use the t-test. And with this, you have the option of doing data, which is where you'll put in the mu naught and then list L1. So like I said earlier, you can just put, if they give you a list of points like the 15 here, I could list all those in L1. Under frequency, you can just put 1, by the way. Don't worry about that, just leave it as 1. But you just plug in the mu naught, the null hypothesis is mu. You put in the list where you have entered all the data, and then put your alternative, whether it's not equal to, less than, or greater than, and then run it. So that's option 1 to do the data, but you can also do it over with stats. So if you have the x bar, the sample standard deviation already computed, you can just plug those in, which is a lot faster than plugging in all the data. But if you don't have these yet, you'll have to plug in all the data to get them anyway. So you got either option when you're using that. Okay, well that's all, and good luck. Just 3 problems tonight for homework.